All right, so I'm hoping this is going to pick up well enough. We have a long coil here. It's sort of tied down at the other end. That is known as a fixed end over there because that end is not really free to move. So I send a wave down, and so part of what I want you to observe is what sort of happens here. It's now farther away, and I'm hoping I'm seeing what's going on here. Let's see. I have a long coil here, and it's going to produce a transverse wave. I have a long coil here, and I'm going to send a pulse down. And so the big question is what happens when the pulse gets down to the other end. So I can see if I can do this without interfering. And you might be able to see it a little bit better. Let's see if I can get a straight on shot here. So when I send a pulse down, what happens when the pulse gets to the fixed end down there? Well, yeah, I think you can clearly see it there. It does reflect, and that's one of the properties. When you hit a boundary, part of it will reflect. But notice that I'm sending the pulse down on this side over here, but the reflection comes back on this side over here. And that is one of the properties of when you hit a fixed boundary. Stupid COVID-19. When you hit a fixed boundary, it will reflect back on the opposite side. In other words, it will invert. Now, if I send a second wave down, it's going to interfere with the first wave. So think about it, when the two waves meet, what is going to happen here? Well, it's not necessarily easy to tell right there, but if you do send waves coming in from opposite sides, and I think we might be able to do a quick demonstration here. So I've got a really short little bit right here. Yep. I send a wave. Matter of fact, I'm going to send a wave from both sides. So all I'm doing is just a small little pulse like that, and I send a small little pulse from both sides. But when they meet, it gets bigger than it was before, and hopefully it can be seen in the video. So a small little pulse, both sides, but together it produces something bigger than before, and that's known as constructive interference. Now, if I send one down and the other one up, when they meet in the middle, notice that it just looks like it's twitching. The middle doesn't move very much, and that's because it's destructive interference. So what I'm going to do is I'm going to send a wave down. It's going to hit the other side and reflect back on the opposite side. I'm going to send the next wave down, and send the next wave down, and it's going to interfere with the first wave. And matter of fact, if I keep sending it just the right way, what we have here is known as a standing wave. There's that point in the middle, which isn't moving very much. That's known as a node. There's a node on the other end, and technically there's a node where my hand is right here, you know, as best as I can. Now there are those other points that are swinging very widely, which goes from constructive to destructive interference. Those places right there, which have the biggest variance, are known as antinodes. Now, the simplest pattern I can get here with the two fixed ends, my hand being one fixed end and the umbrella stand being the other fixed end, that's the simplest pattern. It's not necessarily the simplest to do on concrete, but that's the simplest. That's known as the first harmonic. Let's see if we can get the whole thing in. So we have one antinode in the middle, two nodes on the ends, and then the next simplest, this is the second harmonic. If I increase the frequency, and I'm going to have to, all right, so if I increase the frequency, and take 3, if I increase the frequency, there we go, we have a third harmonic, where we have 3 antinodes, we have 4 nodes. If I increase the frequency even more, 1, 2. I'm going to have to check the video later, whether that's the 4th harmonic or 5th harmonic. I had it for just a brief while. My arm does get tired, and that was my left arm, so that was a little bit more difficult. And so we've got, oh, and the other thing is, all right, I'm holding this right here. I'm holding the, and I'm going to send a pulse down and just sort of keep sort of a mental note of how fast that wave travels. I'm tightening up the spring, and I send the pulse down again. Again, think about how fast that's traveling. And I'm keep tightening it more and more, so let's tighten it even more. So as I tighten the spring, the wave really does seem to be traveling faster. All right, so this makes sense that the tighter it is, the faster the wave moves, because if you think about it, for a transverse wave, which is what we're demonstrating here, for a transverse wave, as a coil moves perpendicular to the motion, so as this is moving this way, how quickly the next one responds to it is related to how much tension there is between it. What is the pull that one coil has on the next coil? Because I'm not physically touching down there, but obviously I affect what's happening down at the other end. So transverse waves depends upon how much one particle will pull on the next particle. So it basically pulls up, and then when it comes down, it pulls them back down. Unlike the longitudinal wave, which is dependent upon how much one will push onto another one instead of pull. And presumably there's something else I've forgotten, but we will see how that goes when I actually look at this on the computer. Basically what I have down there is a free end, because the end is free to move, thus it's called a free end. And notice what happens when I send a wave down to a free end. See if I tighten up a little bit, do I get it? So on what side does the wave return?